You're here because you want to get up to speed on important stuff fast, and today we're diving into something that's everywhere but usually invisible until, well, until it goes wrong. Software.
Right, and not just glitches, we're talking major software disasters, failures with really serious, sometimes tragic consequences.
Exactly. And what's fascinating is when you line these incidents up, you start seeing these patterns emerging. It's pretty eye-opening.
Yeah, we've pulled together details on 10 big ones for you. Think of this as your rapid guide to the core issues and, more importantly, the lessons learned.
So our mission today, cut through the tech talk, the blame games, and really distill what went wrong in these 10 cases. We want to pull out those recurring themes so you walk away with a solid grasp of software risks and, maybe some best practices.
Okay, sounds good. Where should we start?
Let's kick off with a really major one, still fresh in many minds.
Yeah.
The Boeing 737 MAX crashes.
Ah, yes. A truly sobering example. We're talking 2018, 2019 Lion Air Flight 610 and Ethiopian Airlines Flight 302. Brand new Boeing 737 MAX eats.
And tragically, 346 people lost their lives. The software system involved was MCS, right? The Moving Characteristics Augmentation Software.
One MCS. Its purpose, basically, was to make the MAX handle more like earlier 737s because the new, larger engines changed the aerodynamics a bit.
So it automatically pushed the plane's nose down if it thought the angle of attack, the nose angle, was too high to prevent a stall.
Correct. But here's the critical design flaw. It relied on data from just one angle of attack sensor. A single point of failure.
Just one. Wow. It's like having a safety system that only listens to one opinion, even if that opinion is wrong.
Precisely. And if that single sensor malfunctioned, which it did in both crashes, it fed bad data to MSAS.
Triggering the system unnecessarily.
Right. Even when the plane was flying normally. And what made it even worse, the pilots barely knew it existed.
That's the part I still find hard to believe. It wasn't clearly documented in the manuals, not covered properly in training.
Shockingly, no. So you have pilots fighting an invisible system based on faulty sensor readings, pushing the nose down again and again. They were trying to regain control, but MSAS kept activating against their inputs.
A horrific scenario.
Absolutely devastating. The aftermath, of course, was huge. The entire MAX fleet grounded worldwide, billions in losses for Boeing.
CEO ousted. Massive reputational hit.
And significant changes followed in aviation regulations, software certification, pilot training, all stemming directly from this.
So the key lesson here, crystal clear. The immense danger of single points of failure in safety-critical systems and the absolute need for transparency. Operators have to know how these systems work.
They need to know how they function and, crucially, what to do if they malfunction. It can't be a black box.
This really sets the stage. Even in tightly regulated fields, software plus information gaps can be catastrophic. Makes you wonder about redundancy and transparency in other critical systems.
It really does. It's a fundamental question.
Okay, let's shift gears, go back a bit further. Therac 25, mid-80s. This one is chilling. Software bugs directly harming patients.
Yeah, the Therac 25 radiation therapy machine. Between 85 and 87, at least 6 patients received massive radiation overdoses during cancer treatment, severe injuries, even deaths.
And it wasn't a mechanical failure like a broken gear or something. It was the software controlling the machine.
Exactly. The embedded control software was the root cause. There were a couple of key issues. One was something called a race condition.
Race condition.
Yeah.
What's that? Yeah, it's simple terms.
Imagine 2 commands trying to happen at the exact same instant. Depending on tiny timing differences, which one gets there first by microseconds, the machine could end up in a completely unintended, and in this case, dangerous high-power state.
Okay, so unpredictable behavior based on timing.
Right, and crucially, the Therac 25 design had removed hardware interlocks that were present on earlier models.
Hardware interlocks, like physical safety switches.
Yeah, physical mechanisms designed to prevent the machine from firing in an unsafe configuration, regardless of what the software said. They took those out, relying purely on the software for safety.
That seems incredibly risky for a radiation machine.
It absolutely was. And compounding this, the software development process lacked rigor. No formal testing, no peer code reviews to catch these flaws.
So bugs just slip through.
They did. Even the user interface was confusing. It didn't always clearly show the machine's actual state, sometimes giving misleading error messages.
The outcome was just terrible. Lawsuits, suffering, a huge blow to trust in medical tech. It's often cited as a landmark case, right?
Yeah.
One of the first really showing software could be lethal.
Definitely. The big takeaway. You need both software and hardware safety measures. Redundancy is key.
Don't rely solely on the code.
Never. And it hammers home the need for formal methods, rigorous testing, code reviews, thinking through every possible state, especially when lives are at stake.
Essential lessons. Okay, let's move to a different domain. Military tech. The Patriot missile failure during the first Gulf War, 1991.
Ah, yes. Iran, Saudi Arabia. A U.S. Patriot missile battery failed to track and intercept an incoming Iraqi Scud missile. Tragically, 28 U.S. soldiers were killed on the ground.
And the cause wasn't a big complex bug, but something subtle in the system's clock.
Exactly. It came down to how the system's internal clock handled time, specifically using floating point numbers.
Floating point numbers with decimal points.
Right. The way computers store and calculate these isn't always perfectly precise. Tiny, tiny rounding errors happen with each calculation, each clock tick.
Usually insignificant, I guess.
Usually. But the Patriot system had been running continuously for over 100 hours. These minuscule errors accumulated, they added up.
How much did they add up to?
Enough to cause the internal clock to drift by about 0.34 seconds.
A third of a second. That doesn't sound like much.
Not in everyday life, no. But when you're trying to calculate the trajectory of a Scud missile traveling at Mach 5, that third of a second is huge.
Ah, okay. It throws the prediction way off.
Precisely. The system miscalculated where the Scud would be, looked in the wrong patch of sky, and failed to engage.
Leading to that tragic loss of life. I remember the questions afterwards about military software reliability.
Yes, it led to congressional scrutiny, reviews of testing procedures. The key lesson is stark. For time-critical, safety-critical systems, even tiny cumulative errors matter.
So you need ways to handle that.
Right.
Like regular resets or corrections.
Exactly. Regular system reboots would have reset the clock error, or software designed to account for and correct this drift. Precision is non-negotiable in these contexts.
Another powerful example. Okay, let's shoot for the stars, or rather where a star-bound mission went wrong. Ariane 5, Flight 501, 1996.
A very dramatic, very expensive failure. The European Space Agency's brand new Ariane 5 rocket blew itself up just 37 seconds after launch.
Wow, 37 seconds. And the cost was enormous, right?
Around $370 million, including the rocket and its satellite payload, gone. And the cause wasn't entirely new code, was it? It involved reusing software.
That's the crucial part. They reused the inertial reference system software, the navigation software, basically from the older Ariane 4 rocket.
Seems logical, right? Save time, save money, use proven code.
In theory. But the Ariane 5 was a different beast. It accelerated much faster off the launch pad than the Ariane 4.
Okay, and the old software couldn't handle that. Not quite. There was a specific data conversion step inside the software. It took a 64-bit floating point number representing horizontal velocity.
Okay, a big detailed number.
And tried to convert it into a 16-bit signed integer, a much smaller, simpler number format.
Right.
On Ariane 4, the velocity values always fit within that 16-bit range. But on Ariane 5, with its higher acceleration, the velocity value got too big.
It wouldn't fit.
Exactly. It caused an overflow error, like trying to pour a gallon of water into a pint glass.
And that single error brought down the rocket. Wasn't there any safety mechanism?
Yeah. There was code to handle such errors and exception handler. But get this. It had been deliberately disabled for this part of the flight sequence on the grounds it wasn't needed after liftoff and might affect performance.
Oh, wow. So the safety net was turned off.
Yes. And to make matters worse, the Ariane 5 had redundant navigation systems.
Oh, backup.
Right. But both systems ran the exact same software, hit the exact same overflow error at the exact same time, and failed identically.
Unbelievable. Redundancy defeated by a common software flaw.
Precisely. The lesson from Ariane 5 is a huge warning about reusing legacy code. You must revalidate all assumptions and constraints in the new environment.
Can't just copy-paste and hope for the best.
Absolutely not. Rigorous testing in the new context is essential.
A very expensive lesson indeed. Let's stay in space for our next one, the Mars Climate Orbiter, 1999. Another costly failure, but this time. The cause was almost embarrassingly simple.
Embarrassing is one word for it, yeah. Painful for NASA, certainly. The $327 million Mars Climate Orbiter disintegrated when it entered the Martian atmosphere, not because of a complex bug, but a units mismatch.
Units, you mean like metric versus imperial?
Exactly that. The ground software team at Lockheed Martin, who calculated the spacecraft's thruster firings, provided the data in pound seconds, the imperial unit of impulse.
Okay.
But the navigation software on board the spacecraft, built by NASA's Jet Propulsion Laboratory, expected that same data in Newton seconds, the metric unit.
Seriously,
And
they were using different measurement systems.
yes, and critically, there was no check built into the interface between the ground system and the spacecraft software to verify the units.
Nobody thought to double-check if they were speaking the same language.
Apparently not in this specific interface specification. So the spacecraft interpreted the thrust instructions incorrectly. Each thruster firing nudged it slightly off course based on the wrong force value.
And over the long journey to Mars.
Those small errors accumulated, causing the orbiter to approach Mars at a much lower altitude than planned. It hit the atmosphere too low, too fast, and burned up.
A mission lost over pounds versus newtons. That's quite something.
It really is. The lesson is fundamental. Meticulously validate all interface specifications between different systems or teams, units, data formats, everything.
Assume nothing.
Yeah.
Check everything. Contract testing, you called it.
Exactly. Define the contract between software components, what data goes in, what comes out, in what format, and test that contract explicitly. Prevent these basic but catastrophic misunderstandings.
Right. Okay, let's come back to Earth. Financial world this time. Knight Capital, 2012. A trading glitch that almost wiped out a major firm in minutes.
A truly stunning event. August 1st, 2012. In just 45 minutes, Knight Capital lost $440 million. Pushed them to the brink of bankruptcy. And the trigger, a software deployment error?
So not the code itself initially, but how it was rolled out.
Precisely. Knight was updating its trading software across multiple servers. The deployment script, the automated process doing the update, it failed on one of their 8 servers.
Just one server missed the update.
Yep. So that one server was left running old code, and this old code contained a feature, a testing routine called PowerPeg, that was supposed to be long gone.
And this old code got activated somehow.
It did. When the rest of the system went live with the new software, some signal inadvertently triggered this dormant PowerPeg routine on the unupdated server. And it went haywire.
What did it do?
It started flooding the market with erroneous orders, buying high, selling low, just churning trades automatically at immense speed. The market was overwhelmed.
And Knight was on the hook for all those bad trades.
Exactly. Racking up those massive losses in under an hour, they needed a bailout to survive.
Incredible. What does this tell us about software deployment, especially in high-speed environments?
It screams the importance of robust deployment strategies. Things like blue-green deployments, where you deploy to a parallel environment first, test it, then switch traffic over.
So you can easily switch back if things go wrong.
Right. Proper versioning, automated checks to ensure all servers are updated correctly, and having solid tested rollback plans are crucial.
It also makes a case for that chaos testing you mentioned, like just deliberately simulating failures.
Absolutely. Testing what happens if, say, one server doesn't get the update. Could we detect that? Could we isolate it quickly? Knight Capital highlighted the need for that kind of resilience testing.
Makes sense. Okay, staying with finance, but broadening the view. The 2010 flash crash. This wasn't just one firm. The whole market went crazy for a few minutes.
Yeah, May 6th, 2010. A truly bizarre and frightening few minutes. The Dow Jones plunged nearly 1,000 points, erasing about $1 trillion in market value before recovering significantly.
$1 trillion. Gone and then back.
Yeah,
What caused that? Was it software again?
Software played a huge role, particularly the interaction between different types of automated trading systems. The initial spark seems to have been a single, very large sell order for E-mini S&P 500 futures placed by a mutual fund using an algorithm.
Okay, a big automated sell-off.
But the algorithm apparently didn't adequately account for market liquidity, how many buyers were actually available at current prices. It just kept selling, pushing prices down rapidly.
And then other algorithms reacted.
Yes, particularly high-frequency trading HFT algorithms. These systems are built for speed, executing and canceling orders in milliseconds. As prices started falling, many HFT algos likely amplified the drop. Some might have withdrawn liquidity, making it harder for prices to stabilize. Others engaged in what's called hot potato trading, rapidly passing orders back and forth, adding to the volatility.
So it cascaded. One big sell order triggered a chain reaction among the super-fast HFT bots.
That's the general consensus. Liquidity just vanished. Prices plummeted in a feedback loop. It exposed the fragility that can emerge from these complex high-speed interactions.
And the aftermath. What changed?
Regulators like the SEC and CFTC brought in circuit breakers, automatic trading halts triggered by rapid price moves designed to give the market a pause during extreme volatility.
A kind of emergency brake.
Exactly. The flash crash was a massive wake-up call about systemic risk in algorithmic markets. It showed the need for better monitoring, controls, and understanding how these systems interact at scale.
You need controls not just on individual algorithms, but on the whole ecosystem.
Precisely. Auditing for systemic risk, not just individual bugs.
Fascinating. And a bit scary.
Yeah.
Hey, let's shift to public services. The London Ambulance Service CAD failure, 1992. A failure in an emergency system with dire consequences.
A truly tragic case. The rollout of a new computer-aided dispatch, or CAD system, for the London Ambulance Service in October 1992 was disastrous. It's estimated that the system's failures contributed to delays that may have caused between 30 and 45 deaths.
30 to 45 deaths linked to a dispatch system. What went wrong?
The system, called LASCAD, was fundamentally flawed and critically inadequately tested. It simply couldn't cope with the real-world workload of London's emergency calls.
It failed under pressure.
Dramatically. Dispatchers reported the system losing track of ambulances, allocating multiple ambulances to the same incident, or failing to dispatch one at all. Some emergency calls reportedly went unanswered for hours.
That's horrifying.
Yeah.
Were there underlying technical issues?
Yes. Reports mentioned memory leaks causing the system to slow down and crash, interface problems, and just generally unstable software. Crucially, the system was rushed into service before it was truly ready.
Rushed. A common theme in some of these failures.
It is. The pressure to go live often overrides prudence. The LASCAD system eventually had to be scrapped entirely. There were inquiries, resignations, a total system failure.
The key lesson seems obvious but vital.
Absolutely vital. Critical infrastructure software, especially for emergency services, must be rigorously tested under realistic, high-stress conditions. You need robust fallback procedures.
Lives depend on it. You can't cut corners.
You simply cannot. Stress testing, proper load testing, and phased rollouts with manual backups ready, these are non-negotiable.
A stark reminder. Now, for a very different kind of disaster, one that unfolded over many years, the Post Office Horizon scandal in the UK.
Ah, Horizon. This is less a single crash and more a slow-motion catastrophe, a profound miscarriage of justice fueled by faulty software and institutional denial. We're talking from 1999 right up to 2015 and beyond.
And it affected hundreds, maybe thousands of people, sub-postmasters.
Over 900 sub-postmasters people running local post office branches were prosecuted by the post office itself for theft, fraud, and false accounting. The evidence came from the Horizon IT system supplied by Fujitsu.
But the system was wrong.
The Horizon system was riddled with bugs, prone to errors, and frequently generated phantom shortfalls in branch accounts, money that wasn't actually missing.
So the computer said money was gone, but it wasn't.
Exactly. But the post office management adopted this stance that the Horizon system was robust, infallible even. They refused to believe the sub-postmasters who insisted they hadn't stolen anything and that the system must be wrong.
They trusted the machine over their own people. That echoes the Therac 25 operators or even the 737 pilots initially being dismissed.
It's a disturbing pattern, isn't it? This blind faith in the technology, or perhaps a refusal to admit the technology could be flawed. The post office pursued prosecutions relentlessly.
And the consequences were devastating.
Utterly. Hundreds wrongfully convicted. Over 230 people were imprisoned, families ruined, reputations destroyed, homes lost. There have been suicides directly linked to the stress and injustice. It's one of the UK's biggest ever scandals.
It's just staggering. What's the fundamental lesson from Horizon?
Never, ever assume software is infallible, especially when it's used in the justice system or has life-altering consequences. There must be transparency, auditable logs, pathways for challenging the data, and independent verification.
You need checks and balances, and you need to listen when users report problems.
Absolutely. The human cost of institutional denial and buggy software in this case is almost immeasurable.
Truly shocking. Okay, let's wrap up with one more, a widespread security vulnerability. Heartbleed 2014.
Heartbleed was a different kind of disaster. Not a crash or direct physical harm, but a massive data exposure risk affecting a huge chunk of the internet. It was a bug in OpenSSL.
OpenSSL. That's core internet plumbing, isn't it?
Yeah.
Used for secure connections, HTTPS.
Exactly. It's an open source library used by countless websites and services to encrypt communications. The Heartbleed bug, discovered in 2014 but existing for about 2 years prior, was in a feature called the Heartbeat extension.
Okay, what did this bug do?
Essentially, due to a missing bounds check, a failure to verify the size of requested data, an attacker could trick a vulnerable server into sending back small chunks of its private memory.
Its memory. What kind of stuff is in there?
Potentially very sensitive stuff. Private SSL keys, the keys that prove a website's identity and encrypt traffic. Usernames, passwords, emails, instant messages, business documents. Basically anything that happened to be in that chunk of memory at the time.
Wow, like leaving the server's brain exposed.
That's a good analogy. And because it left no trace in typical logs, attackers could have been quietly siphoning data for 2 years. At the time of discovery, it was estimated something like 2/3 of the internet's web servers were vulnerable.
2/3. That's immense. What was the fallout?
A global scramble, emergency patching of servers, mass revocation and reissuance of SSL certificates, widespread advice for users to change passwords everywhere. The cleanup cost was estimated at over $500 million.
And it highlighted issues with how critical open source software is maintained.
Definitely. OpenSSL, despite being vital infrastructure, was chronically underfunded and maintained by a small, mostly volunteer team. Heartbleed spurred conversations and initiatives to better support and audit critical open source projects.
So the lesson.
Critical infrastructure, even if open source, needs resources. It needs thorough auditing, testing, maybe even formal verification. And it highlighted the ongoing importance of memory safety programming practices that prevent these kinds of memory access bugs.
Okay, so 10 disasters. Boeing, Therac 25, Patriot, Ariane 5, Mars Orbiter, Night Capital Flash Crash, London Ambulance, Horizon, Heartbleed. Quite a list.
It really is. And stepping back, despite the diversity, aviation, medicine, military, space, finance, public service, internet security, those common threads are striking.
Yeah, let's recap those. Single points of failure, right? Keep showing up.
Definitely. The danger of relying on one sensor, one system, one piece of software without adequate backups or checks.
And testing. Rigorous, realistic testing. Not just checking the boxes, but really pushing the system, thinking about weird edge cases, stress conditions.
Absolutely. Like the London ambulance system failing under load or Ariane 5's assumptions not holding in a new context.
Right.
Insufficient testing is a recurring theme.
Communication and transparency, too. Pilots not knowing about MSICAS, sub-postmasters being ignored by the post office.
Yeah, the interface between the tech and the humans using it or being judged by it is critical. Lack of transparency, lack of clear documentation, dismissing user concerns leads to disaster.
And underlying all of this,
Yeah.
the very real human cost. Lost lives, ruined livelihoods, broken trust. It's not just about code, it's about people.
Precisely. These aren't abstract technical failures. They have profound real-world impacts. Like we saw with Therac 25 and Boeing, that over-reliance on just the software or just the operator without acknowledging the whole system, it's a recipe for failure.
So reflecting on all this, it really poses a challenge, doesn't it? As software gets more complex, more embedded in everything we do, what's our collective responsibility here? For developers, for companies, even for us as users?
That's the big question. How do we build, deploy, and manage this increasingly complex software world more safely, more reliably, more justly?
And given these past failures, what are the really tough questions we should be asking now about the technology we rely on every day? Something for everyone to think about.